Uh, Good evening, everyone, and welcome to the next session, maybe today's session of the Exoplanet course. And we are towards the end of the course. Today is the second last session. And today we have with us Dr. Prabal Saxena. I would request Dr. Ravi to kindly introduce Dr. Prabal.
Good evening, everyone. Welcome, Prabal. Dr. Prabal Saxena is a civil servant and a research scientist at NASA Goddard Space Flight Center. Prabal is probably one of the very few highly interdisciplinary research scientists that I've known, actually. He works on exoplanets, planetary science, moon, you name it, and he does it. So he's a master of everything. So Prabal is going to talk about exoplanet missions today. So Prabal, when you're ready, please go ahead.
Great, thanks, Ravi. Hi, everyone. My name is Prabal Saxena. I'm like Ravi mentioned, I'm a planetary scientist at NASA Goddard. I work in the laboratory of planetary geology, geophysics, and geochemistry. And like Ravi mentioned, I'm interested in planets in general, and also the moon. I do a lot of research related to that, but exoplanets are one of the first things that I really started working on. And so I'm happy to be talking about missions today and kind of talking about them maybe in a slightly different perspective, in addition to talking about details behind some of them. So just to let you all know, the way I plan to kind of talk about these missions is I have about 30 slides. So just to let you know, as you start to nod off in the middle of it, and I'll try to, every 2 slides or so, try to make sure that there's a little bit of a gap where if you want to ask a question, feel free to raise your hand or just be like, hey, Prabal, just a quick question on something about, one of the other slides or something like that. And I will make these slides available at the end. So one of the things you'll notice is that for each of the missions that I describe, these missions are really, really powerful missions that have made great discoveries with respect to exoplanet research, but there's also a lot basically in just about every one of them. So it's pretty hard to fit that within 1.5 hours. So what I've done is I've put basically links to each of the missions so that you can go and explore more information about them. If one is particularly appealing to you, if one is maybe more relevant to your expertise already, or you want to learn more about it, you can kind of use that. So just to get started, I'm going to talk a little bit about what I plan to discuss in this particular lecture. Now, you've been learning about exoplanets for this entire course, so I'm going to generally assume you know what an exoplanet is, but in case anybody needs a refresher, I'll spend a very short period of time talking about what an exoplanet is, and then I will spend an even shorter amount of time, but I will make sure to mention why I am giving this lecture, why it's important to me, and why you might see it set up in the way that it is. Then I will talk about really the meat of this particular lecture, which is selected past, present, and future mission capsules. So basically a little bit of information about how the missions were set up, how they were expected to operate, what their instrumentation was, what their orbit was, and what their goals were. And then typically, especially if they're already past or current missions, I will discuss what exactly they've already discovered, what they're in the process of observing. And then finally, I'm going to talk a little bit about something that I think is really just as important as these kind of mission capsules, which is that the idea that creativity really underpins a lot of exoplanet exploration. I think that's probably true in general planetary science, but I really want to emphasize that, and you'll see why in the motivation. I think it's because it's the type of thing that you might occasionally see, all right, well, these are the types of things I need to do in order to analyze data or in order to produce a good model. But really, one of the exciting things about trying to interpret exoplanet detection data or trying to characterize an exoplanet is trying to understand how you can glean additional information, how you can learn more about these planets by thinking about the data they might give in a way that is completely unique or it hasn't been thought of in a particular way before. So I've kind of broken that into a couple different things in terms of subcategories, but it shouldn't be, it's kind of more a hodgepodge of different things. So just to go ahead and start, hopefully you all know exoplanets are just planets that are beyond our solar system that are not orbiting the sun. So they can either be orbiting other stars, they can be free floating planets. And if you look on the left, you have this artist's conception of a bunch of different types of planets, and some might be kind of familiar. You might have at this point spend enough time in lectures to be like, all right, these are gas giants. These are things that kind of resemble Jupiter. Some of them might be really close to their stars. So they might be hot Jupiters. Some of them might be really hot rocky planets, which is why you see maybe a really, really bright area on a star facing part of the planet. You might end up seeing something like a lava ocean or something like that. And then there are also some kind of fun visualizations in the top and bottom left, where you kind of see these darker planets that might be those things that don't have a host star that they're orbiting. So that's just a very, very initial, what is basically an exoplanet? You all probably know, I believe you've had a detection method course already, that exoplanets can be detected by a variety of methods. And those methods and new methods that have been formulated, so new ideas that people have come up with, have changed over time. As a couple of those methods have really been the most prominent in terms of discovering exoplanets. So you're probably familiar with, at this point, the transit method and radial velocity methods, which have really, really found the vast majority of exoplanets detected to date, or the vast majority of exoplanet candidates as well. One of the things you'll probably have noticed, you probably went over, is that these different methods are effective over different phase spaces. So for example, currently something like direct imaging is more effective for large or young planets that are at reasonably large orbital separations from their host star, whereas the transit method tends to be biased towards close-in planets, and again, kind of large planets, which is why hot Jupiters end up being such an easy planet, or relatively easy planet to find in the case of something like the transit method. Finally, like you can see on this left screen, exoplanets are diverse. So we're really excited, and I know Ravi probably talked your ears off about Earth twins, so planets that might be habitable, that might exist in a habitable zone, depending on how you define that, and depending on what you think are the properties of the planet itself. But there are so many different types of planets that it's actually one of those things that's, you can kind of dream up a planet, and then you can kind of go out and look for it and say, hey, could I find a planet that's disintegrating? Can I find something that is lighter than any of the solar system planets? Can I find something that has really, really weird chemistry that I should not have expected, that you don't see in the solar system? And you can often find those planets. So that's a pretty exciting thing too. It also shows that there are a wide variety of ways that planets form and then evolve, which is obviously an entire field, subfield basically in exoplanets. Just a little more information on an exoplanet and really exoplanet characterization. So you probably talked about exoplanet detection methods, and characterization is kind of that next step. I'm hoping that's been kind of sprinkled in terms of how exactly you would try to interpret signals from a planet in order to kind of infer its atmospheric or surface properties. But really, there's some basic properties that you need to know about a planet in order to start to intelligently characterize it. So some of those are mass, volume, and then the density of the planet, because that tells you, are you looking at a rocky planet? Are you looking at a gaseous planet? Are you looking at a planet with maybe some mixture of those two? And then after that, you could also want to try to determine some of the things that we probably conventionally think about characterization, which is surface and atmosphere properties. So that's on the left, you can see is the planetary spectrum generator, which is a really nice radiative transfer tool model. And basically what you can do is you can put in an input atmosphere. So you can see I have a pressure temperature profile kind of cut off by the spectra on the left, and right next to it, vertical mixing ratios for a bunch of different constituents in the atmosphere as a function of pressure height. And what you can see on the top left portion of that that's overlaid over it, this is actually for the planet GJ1214b. I don't know if you've heard of that, but it's expected to be the super Earth that's kind of a water world. And here you can actually use this particular website, this particular tool, to simulate spectra, given really a wide range of different types of observatories, different types of instruments, given a particular set of surface and atmospheric properties. So this is actually a really powerful tool. You get a chance to use it. Maybe people have already talked about it. It's pretty easy to use too. There are a lot of great videos that show you how to use it. And you can make like a plastic planet if you wanted to, and see what that looked like. The other thing that people may not often think about for exoplanet characterization is that one thing that is absolutely becoming the provenance of characterization of understanding exoplanets is how they evolve over time. And there are kind of two ways to think about that. One, at this point, there's enough kind of resolution, there's enough ability in terms of sensitivity with current and new instruments that you can actually start to look at things like exoplanet weather. You can try to determine how the atmosphere actually changes over time, which is a pretty exciting thing because one, it's kind of cool just to see something, changing in front of your eyes outside our solar system. But it's also really, really important because it can help you understand what's going on in terms of that atmosphere, in terms of that surface, because the weather is going to be kind of driven by those properties. The other thing is that as you probably hopefully think about our solar system too, all these planets have been evolving over time. So for example, if you look at the Earth, hopefully you had lectures kind of talked about this as well. 2 billion years ago, we barely had any oxygen in our atmosphere. 4 billion years ago, we probably had no, or 3.5 billion years ago, we probably had no oxygen in our atmosphere. And that's because the Earth's atmosphere evolved, the redox state, surface properties, all these things evolved over time as it kind of went through this thermochemical evolution. And that is the type of thing that probably occurs for every other planet too. So that's exciting because, again, that tells you kind of how these systems form, how they evolve, and how they might either lead to habitability, how they might not, why you might see them be the types of planets they are today. So that's another way in which we try to think about exoplanets. So just really quickly, I'm going to go through these other portions. So understanding these planets, this is why we're talking about missions, usually involves interpretation of direct or indirect signals to infer properties about these worlds. And that usually requires mixing together models with laboratory data and with observations. So really observations are what underpin understanding something else, but then you need to have context in order to interpret what exactly is going on. And that especially helps you then be able to say, all right, well, this model with oxygen fits better than this model without oxygen in the atmosphere. And often, if you have multiple types of observations, if you have multiple observatories, and if you look at different spectral ranges, that can be really key to actually extricating some of the properties of a planet. So I'm going to stop really quickly. Basically, just the first time I'm going to explicitly mention this, but so right now you can see I talk a lot and I talk continuously. But if you have any questions so far, let me know. And if you do not want to butt in and say anything, you can put it in there, and maybe Ravi or Gayatri or somebody else can ask them as well. Because I don't want you to forget any questions, and especially as we get through some of these objects, I will make sure that we kind of go over those before we go to the next slides. So, yep, go ahead.
Hello, Professor. Yeah, I had a doubt. When you were talking about the direction techniques, you mentioned that direct imaging is mostly done for young and big planets. So I was just wondering why you used the word young, like why not old? And also, like, I understand that it's a bit difficult to determine the age of a planet or a system. So yeah, I was just wondering about that.
Yeah, that's a great question. Yeah, it might be, and I'm not somebody who's like, oh, I only like young planets or something like that. The reason why I use young is because especially if you're right now sensitive to larger gaseous planets. So when gas giant planets, even ones that are not hot Jupiters, initially form, they still have a residual heat from their formation. As a result, their temperatures are higher. So you can imagine, because their temperatures are higher, they're giving off more light, particularly if you're looking in the infrared using ground-based telescopes. And what that means is that if your temperature is now higher, you are putting out more light relative to the star than you would have been putting out if you were older and a colder planet. So all of a sudden you're easier to detect. So that's really the main reason why I talk about kind of young planets. It's not necessarily that, we'd love to find more young planets, because then we kind of get this snapshot over time of how planets evolve. And that's really, really interesting to a lot of scientists. But with respect to why they're maybe easier for direct imaging, it's mostly because their thermophysical properties are kind of making them easier to detect using direct imaging. And to know how they're young, that's a great question too. And there is the ability, this is kind of a can of worms, there's the ability to look at stellar rotation, look at models, and to kind of put an age, what you might think an age is of a system. But for direct imaging, for nearly all these systems, the ways they often figure out this is a young system is by looking at the groups of stars that they're in. So they look at these co-moving groups, they say, hey, let me look at an HR diagram, let me see how it falls off. And I know that this particular set of stars, they all formed from the same nebular cloud. So they're all maybe 150 million years old or under 100 million years old. And that's basically how they identify whether they're young or not. So any other questions? All right, perfect. So I'll go ahead and that's exact. Oh, so I see a hand being raised. That's excellent too. Go ahead, Sri Krishna.
Yes, can you hear me?
Yep, perfectly.
Yes. Okay. So my question is, I read an article about how exoplanets can be used as dark matter detectors. So I just wanted to, because linking to the change in temperature when they interact with dark matter. So I just wanted to know your opinion if interdisciplinary studies like this, what the scope of it is, and something about that.
That's a great question. So on specific dark matter, whether they can be used as kind of a means of measuring dark matter. So again, this is probably based upon the idea that dark matter, if you have enough accumulation and if you're, proximity, if the dynamics work out well enough, you might be able to see orbital effects. You might be able to see things that kind of have effects on, I'm guessing, system properties as opposed to planetary properties. Though I'd probably need to look at the article. Whether they're worth studying, let's go to the next slide. It's perfect time. So hopefully if there are no more questions, or if you can hold on for a couple slides, I'll go and talk about that. So why am I giving this lecture? The reason I'm giving this lecture is I'm greedy. I want to learn about exoplanets, and I want people who are creative and excited about them to figure out interesting ways of interpreting them. So when I was talking about those kind of last slides in terms of creativity, you can go and you can use these models that are pre-existing. You can use ways that people have already discovered, and you can do a great job interpreting exoplanets, learning about them, detecting them. But the things that really excite me are basically new and innovative ways of understanding exoplanets and how you can either kind of understand them or you can use them to understand kind of the universe around you. So is it worth it? Absolutely. It's worth studying something like that. Now, I will caution you, if you are trying to do a program, if you're trying to put in a proposal or something like that, if you have a creative idea, that's great. But being kind of creative, as you all might know, can sometimes face a little bit of an uphill battle in terms of being able to actually convince other people. It's worth kind of exploring. And two, you want to make sure you've justified why a new technique or a new concept is worth studying, that you have to kind of be able to show that there is something underneath kind of the idea in terms of the science and motivation and why exactly you quantitatively, for example, might expect that you can use exoplanets as dark matter detectors. So absolutely, totally worth exploring. Maybe don't spend 100% of your time on it, or maybe if you think you have a really great idea, it is worth spending 100%. But it's the type of thing where it's good to think about. I want to be creative, but I also want to think about how well I can justify this with the validity of a particular idea is. So before I take any more questions, I'm going to go and roll through a couple more slides, and I'm going to give you the setup for how I'm going to talk about these exoplanet missions. And then as we get into kind of the capsules, I'll stop and I'll take a couple more questions. Also, if you're too shy to ask a question, or if you don't remember it, or if you're like, I don't know if it makes sense, I will give my email address at the end, and I'm sure Ravi will be able to pass that on too. And you can feel free to email me if you have questions. So really quickly, what you're going to see on these slides for these specific exoplanet mission capsules is in the top left, you'll see basically these two little images. One is of a spectra that you see a trace of from, I believe that's a star in this particular case, but really it's just meant to be a spectra. And then the next to it is this basically filter wheel that has a bunch of filters, color filters. And the idea here is that those two things basically represent, if I have the spectra up there, that means that mission can conduct some type of spectroscopy. Now, the nature of the spectroscopy, it might just be basically spectrophotometry. So basically you might have something that is a prism that divides it into three really big broadband, data points. Whereas other ones might have really great resolution. You might be able to get really nice spectra. And then the photometry basically just says, and that basically you will have some type of filter, some type of bandpass that creates just photometric points, and you don't really get to the point where they're trying to compare photometry at different wavelengths. You're not really even getting spectrophotometry. So depending on whether you see one or both, you'll kind of get a sense of what that mission does. Right below that will always be when was that mission launched, and then what the status was. And on the right here, you can kind of see these are NASA's kind of exoplanet missions from not that long ago. And they also have some ESA partner missions. This image is not an exhaustive list. So it has some past missions, it has some current ones, and then it has some future ones that are being envisioned. And then the same is true for the ESA partner missions. And you also see these NASA Cube and SmallSats, and then all these great ground-based telescopes. But the descriptions I'm about to give are for selected exoplanet missions. So there are a lot of exoplanet missions that have occurred before, that are currently operating and that will occur in the future. And you'll see that in a lot of these cases, this is just a sampling, and some of these were not strictly exoplanet missions, like Hubble and Spitzer, even GWST are not strictly exoplanet missions. They're doing wonderful science regarding galaxies, cosmology, solar system science, just a whole host of other things. The reason why I chose these kind of missions was to kind of give you a taste of what is out there. There are some pretty prominent ones that weren't listed in this. So when I just took it from what I was given as the list of missions, and for example, Gaia, which is a current ESA mission that is using astrometry to find and characterize exoplanets, is a really, really interesting mission, really important mission. You can definitely go look up more information about that, but in this particular lecture, I'm not going to cover that too much. There's no information on RV missions, radial velocity ones, including some that are planned in the future from space. And like I said, not all were primarily designed as exoplanet missions. So it's good to keep that in mind. I'll probably mention that a little bit. So let's see, I think I see a couple more hands in the chat before I start with Hubble. So anybody, if you do have a question, please raise your hand and then I can go ahead and call you and we can talk a little bit about it. Or if not, I can start talking about Hubble, which is totally fine too. All right, great. So let's talk about the Hubble Space Telescope. So I expect some of you might be familiar with the Hubble Space Telescope. Hubble launched in 1990, and here you can actually see it's a cool image where there's an astronaut servicing Hubble. The reason why they were servicing Hubble is once it actually got launched, and it was launched in a low Earth orbit, it had some problems in terms of its optical system and in terms of the images it was producing. The nice thing about Hubble was that it was designed, it was serviceable. So basically, you've had multiple servicing missions where they've been able to switch out instruments, where they've been able to kind of correct things that went wrong as well. Now, Hubble is a 2.4 meter telescope, so that's the mirror size here. I will try to typically give you something that's an equivalent like circular mirror, or I will give you specific dimensions too for a mission. And it has the ability to observe in the UV visible and near infrared. Now, one of the big things about Hubble is it has had about 13 instruments over its lifespan. You'll notice it is still active. So not all instruments are operational right now, but because you're able to change it out, a number of them still are operational. So it's kind of amazing. You have this 30+ year telescope with instruments that are still to this day being used for really interesting studies. So for example, I have a friend of mine, she actually used TESS in order to get UV observations of the Earth as an exoplanet. And the way that she did this was she looked at the moon, and then what she did is she looked at the spectra she got from the moon, took out the moon from a separate portion, and was able to say, oh, well, this remainder is the reflected light from the Earth. So she was able to do this analysis of, hey, what would an Earth spectral look like if I actually wanted to directly look at it? And she was able to get that using Hubble. Hubble's also been used for a number of really kind of groundbreaking studies for exoplanets. So if you all probably are familiar, exoplanets have been discovered for a little bit over 30 years at this point, right around 30 years. And basically from very early on, once these exoplanets were discovered and the concept behind them had been around for even longer before that, people started to say, well, how do I use the instruments that are up there in order to not just discover them, but try to tell something about them? So some of the earliest observations were done using things like NICMOS or STIS or with wide field cameras, maybe though it was the predecessor of WFC3, and they were used in order to understand exoplanets. So in general, you might recognize Hubble as being this great observatory that has the ultra deep field, that has these great images of nebula and galaxies, and it is. But it also has been the type of thing where people have been able to, for example, detect an exoplanet's atmosphere for the first time. So that was done using Hubble. Hubble has been used to detect water vapor, carbon dioxide, plenty of other constituents in the atmosphere. For example, here on the left, you can actually see transmission spectra, which hopefully you know what that is. If you don't, feel free to ask. Happy to talk about that. Of four of the TRAPPIST planets, including 3 of the planets that we think are really exciting in terms of potentially being in the TRAPPIST system's habitable zone. So the TRAPPIST system has a number of small rocky planets that we think are really good in terms of being able to be characterization targets, because the system is relatively close and there's a pretty favorable ratio with respect to the star and planets. And here you can see, now you might say some of these models don't fit really well, but that's probably precision in terms of these kind of data points. But you can see you are getting slightly different morphology for some of these planets. And that kind of shows you that you can start to put some basic detections on what type of constituents do you have? Do we maybe have water in atmospheres? Do we have some of these other constituents? So in addition to kind of looking at atmospheric chemistry, understanding surfaces and atmospheres, Hubble's also been used to probe the structure of disks from which exoplanets form. So there have been a number of studies where scientists have been able to discover or detect planets as they're forming, or who've been able to look at a disk from which you would expect that planets might be able to form from. So this kind of goes back to that question of age of a planet. You actually can start to figure out, well, what is kind of a baby planet? What does a nursery for planets look like? And that's exciting because that then tells you how is material incorporated? How does that kind of control what the chemistry is like? How does that control how exactly these planets might evolve over time? And that's another one of the really exciting things that Hubble's done. It's really a pretty powerful telescope because it has this wide spectral range that it can observe over, and it's a pretty big telescope still. So even though the noise in terms of some of the observations may not be as great with respect to precision as something like GWST, it's still an absolutely powerful tool that scientists use regularly to try to understand exoplanets. So I'll pause for a second with Hubble. Though I will mention that, people often think about Hubble and they think about something like the Spitzer Space Telescope, which is next. So Spitzer is another telescope that is kind of one of these great observatories that has been doing really interesting observations in a lot of different fields in astronomy. It was launched in 2003. It's now retired. Relatively recently retired. And one of the big differences, Spitzer is a little bit under a meter mirror size, and it's an infrared space telescope that was in heliocentric Earth trailing orbit. So that means it was dropped off and it's basically following around Earth, except it's basically dropping off about 0.1 AU every year. Now, Spitzer has 3 instruments that conducted both photometry and spectroscopy. For the instruments that conducted spectroscopy, for example, they were also for the instrument that conducted spectroscopy, it actually had not just spectrophotometric observations, it had higher resolution relative to that, but it lasted for a shorter period of time. So the big thing with an infrared telescope, and particularly telescopes that go out to these longer wavelengths, is that they need to be typically actively cooled, but certainly they require cooling over their lifespan in order to make sure that all the components are at low enough temperatures so that the noise from the heat of your actual equipment, from your instrumentation, does not basically swamp the noise from your signal, from your exoplanet, from your galaxy, whatever you're interested in. So Spitzer actually took up liquid helium, and it was using that as a consumable for a little bit over 5 years in order to cool the telescope down. So eventually that liquid helium ran out, and once it ran out, a lot of those farther in the red wavelengths, it just got too hot to be able to observe anything. And what ended up happening was they didn't stop using the telescope. They realized that there were still 2 bands on the IRAC camera that they could use in this basically new mission, which they call the Warm Spitzer mission. And there have been exoplanet observations made with really both of these kind of phases in both that primary mission for Spitzer and then in that warm Spitzer mission. Now, one of the really exciting things about Spitzer and the fact that you have access to these longer wavelengths than with Hubble is that you were actually able to capture light that came directly from an exoplanet. So if you think about a typical SED just from like a black body, if you have a pretty high temperature planet, if you have a pretty high temperature object, you're going to get basically peaks that are more bluewards. You're going to get more light in general too, right? It's why stars give off so much light relative to planets. So for some particularly hot exoplanets, Spitzer was able to capture light that directly came from those planets. And those were some of the first really groundbreaking observations of exoplanet characterization. One of the things that you can do once you start getting light directly from an exoplanet is you can start mapping basically what the brightness is of the planet across its surface. So this image on the left right here is of HD 1897333b, and it is one of the first maps that somebody created of an exoplanet atmosphere in this particular case. And you can see there's a particular hotspot. You've probably learned about why hotspots are advected in a particular direction, but this shows you that not only was this particular study able to kind of map brightness, but based upon the planetary properties, they were then able to take that brightness map and they were able to say, well, what temperature does it correspond to? And all of a sudden, once you have temperatures that you know as a function of a spatial position on a planet, you can say, how does heat get redistributed on that planet? And you can start to think about, well, what type of atmospheres could redistribute heat like this? So, for example, if you have no atmosphere, you might not redistribute heat that well. So you might have a part of the planet that is facing the star, especially if it's tidally locked, that's really, really hot. Whereas on the night side, which might be like permanent night side, you basically find a much, much lower temperature. Whereas if you have really efficient redistribution of heat, you might have a pretty consistent temperature across the entire planet. Now, observations of Spitzer, they were able to, they did a great job in these cases. All three of these planets I mentioned, they were all gas giants, but they were able to start to determine the rocky nature of, for example, the TRAPPIST planets. There's also an exciting couple studies where they use Spitzer to look at this planet called 55 Cancri E, which is basically this really, really hot, rocky lava world that we expect might have volcanism, certainly has exposed lava on its surface because it probably has surface temperatures in excess of 2,500 degrees Kelvin. So you're talking about temperatures where plenty of metals and other rocks would melt. And Spitzer was powerful enough, especially because these were hot planets, that it was able to basically directly detect light from some of these planets, in addition to also finding transits and doing transmission spectroscopy, but was able to look at them over time. So not only was it able to actually detect and kind of put constraints on temperature and heat redistribution, but it was also able to say, is there potentially variability in some of these planets? And it found evidence in the case of that particular hot planet that there might be some variability as well. So of course, now people are excited about that and they're trying to use GWST in order to kind of understand this planet even more. The other things that Spitzer's been able to do, once you can start looking at temperature, once you can start to probe atmospheric structure like this, one of the cool things, obviously you can start to probe composition. So if you have, for example, molecules that absorb light or whatever else, you might be able to find evidence of them, but you also might be able to start to find evidence of winds. And one, you can put constraints on the evidence of winds based upon where you see these hotspots. And that's something that Spitzer has been able to do in some of these gas giant planets. Spitzer's also been able to help constrain, relatively recently, there's a study that showed that it can help constrain free floating planets, properties with respect to mass and volume. And the way they did this was they actually have microlensing surveys on the surface that are conducted from the ground on the surface of the Earth. But they also, once they found a particular potential planet candidate, they said, all right, let's use Spitzer now, because Spitzer is trailing in a heliocentric orbit. It's so far away that when it can make the detection, if it is a real planet that they might have detected, all of a sudden you have a parallax angle because you're separated pretty far from the Earth. So Spitzer was able to kind of contribute to observations and put constraints on the planet in that particular means. So that's basically, these first two telescopes that I've talked about, which is Hubble and Spitzer, were basically telescopes that were not necessarily designed or were not even really thought of with respect to how they would use them to understand exoplanets. But because they were just powerful tools, and because there's exoplanets out there and they're sending information out to us, we were able to use them in order to really have these profound insights into how into the properties of these exoplanets and into a lot of other things that we wanted to know with respect to kind of the environment that they're in. So I'm going to go ahead and move away now from kind of these early great observatories and start to go to more focused exoplanet missions. So the first focused exoplanet mission I'm going to talk about is the Corot mission. And this is a French and ESA mission that was launched in 2006. It's been retired since then. And it's a much smaller telescope. It's about a little under 0.3 meters. And it's in low Earth polar orbit. And it basically spent its lifetime trying to detect transiting short period terrestrial exoplanets and also conduct astroseismology studies of sun-like stars. So astroseismology studies are just going to be involved, are just going to basically revolve around understanding vibration modes within the star. And they can kind of tell you about fundamental properties about the star and can also help you glean ideas about activity on the star as well. But really, one of the exciting things that Corot was aimed at doing was using visible photometry in order to try to detect planets that were hopefully not just gas giants, because at that point, there weren't that many rocky planets that had been detected. And it also did have a low resolution spectroscopy mode using a prism for the astroseismology. Now, Corot detected over 30 planets. Most of them were still large, hot gaseous exoplanets. And that's because, like I said, they're easier to find with the transit method. But it also discovered a number of really interesting rocky planets. In fact, it discovered the first real rocky planet that was in the super Earth regime and that really had this extensive modeling of multiple components in order to understand what type of surface properties it had. So this planet Corot 7b had this paper by Leger et al., which looked at potential properties given where it was located relative to its star, and was able to model that, hey, this planet probably has a lava ocean. It might have a lava ocean that basically covers half of the planet. And then there was really cool stuff about, what exactly does that mean in terms of an atmosphere? How's material transported to different portions of the planets? How might that planet then, have interesting information that can tell you about its chemistry and how it evolved over time? So those are a couple of things that Corot was able to do in that first planet, and that really kind of set the stage. And I don't want to jump over this too much. So even though it looks like 30 planets for a photometry mission, these are some of the first really key planets that we started to understand. And these are some pretty extreme worlds, because when you are getting these planets that are easier to detect, that means they have to have pretty large signatures, which means that they might actually be pretty good potentially for follow-up. And they also might be really interesting because they are on the more extreme range of things. So Corot really set the stage for the Kepler Space Telescope. So Kepler is another name you might be familiar with, and Kepler is really revolutionary. So Kepler was again, in this case, you'll notice it only had photometry, and it launched in 2009. But it was basically a 1.4 meter visible light telescope. And this was, again, in heliocentric Earth trailing orbit, kind of like Spitzer. And its main mission was to basically look at the sky, and you can see this field of view on the left with kind of the CCDs overlaid on top, right near Vega and right near Cygnus. And it basically was just looking at 150,000 main sequence stars and just staring at them for 3.5 years. Now, the reason why it was doing that was its key goal was to try to find how many Earth-sized planets and larger exist in or near the habitable zone of a wide variety of spectral types of stars. Now, obviously, it really one of the things the mission cared about was stars that were like our own stars, so G-type stars. But really, the idea was Kepler wanted to start to conduct this wide-ranging kind of demography, trying to understand how many planets they are, what types of planets they are, what their sizes are, and how they kind of vary around different stars. Now, by just kind of sitting there with a relatively large telescope in space, Kepler was able to achieve a really great precision, so about 30 parts per million on a 12 magnitude star for about a 6.5-hour integration. So that means for an Earth-sized planet, that gives you an SNR of just under 3 for that particular period. So over a 3.5-year period, and remember, because the Earth takes about a year to orbit the sun, that means you might get 3-ish transits, of a planet that you think might be like the Earth. And you already probably need, you can't just make an Earth detection of an exoplanet with just one transit. You've probably kind of gone over that. So you need multiple transits in order to confirm a planet, confirm its orbit, confirm usually size is something you can do kind of earlier unless you have a specific model that needs to break apart degeneracies. But really, Kepler was aimed at trying to find planets, and it was a different type of mission because it wasn't pointing at different parts of the sky. It was just saying, I don't care about moving to different parts of the sky. I just want to look at this one region and say, what type of planets might I expect? What type of data might I expect from that? So the results were pretty revolutionary. So Kepler spent a little under 10 years in space. It says 530,000 stars here. I'll explain why that star number went up, but it was really about 150,000 stars in that primary mission. And this is the kind of astounding number. Kepler's confirmed, so these aren't just targets or potential candidates, but Kepler observations confirmed over 2,600 planets. And these planets were really, really wide ranging. We're talking about planets that were big, that were small, but we're talking about planets around just about every type of star you can imagine. We're also talking about planets that were in or near habitable zones, or what we think of habitable zones. You probably talked about the different types of habitable zones we think about of their systems. So all of a sudden, we went from maybe handfuls of planets to hundreds of planets to now we have thousands of planets, to the point where you would start to see on some of the main preprint archives, the places where they announce papers, it was a daily occurrence for there to be new planets found. We're basically at that point, which is a really exciting thing, because back in the day, people would get excited and it'd be a discussion point for a week trying to understand the newest gas giant that was discovered. And now all of a sudden, not only are you finding planets, you're finding multi-planet systems. We can actually start exploring really interesting questions like orbital architecture, how exactly planets within one system might vary from one another. So this image on the left, that's kind of zooming out, shows an image of the size of the solar system. And then this is only in 2012. So this is way back. This is not even when a lot of other planets have been confirmed. But basically, this shows the different systems Kepler discovered. Now, one thing you'll notice, a lot of these systems are very, very close in. And that's why when you look at the temperature color coding on the left, a lot of the temperatures on these exoplanets are really pretty high. And you'll also kind of probably wonder, well, there also are cooler ones, and they are at much closer distances than the solar system appears to be. So how does that work? Because you can kind of see the inner solar system versus the outer. And that's because Kepler was able to detect a lot of planets that were basically in multi-planet systems that were around smaller stars. And that's just basically because of orbital mechanics. So if you think about, if I have a star that is an M dwarf and it's a much smaller mass star, one, you might suppose that its molecular cloud from which the planets formed was smaller, and that the planets as a result formed closer in. They probably don't have as many that form much, much farther out. So as a result, if you're trying to use the transit method to find these planets around a smaller star, one, you're more efficient at being able to find planets using transit when your star is smaller, because then the same size planet around a M star would have a larger transit depth than around a G star. But also that means you'll get way more transits. All of a sudden, a planet that might be in the habitable zone around an M dwarf might only need basically tens of days to complete a year, as opposed to something like, the Earth, which is going to take about a year. And if your telescope is only staring for 3.5 years, you might collect a bunch of transits for, a planet around a smaller star than something around a G-class star. So Kepler really revolutionized exoplanets by detecting these thousands of worlds, and it detected them with basically such a diverse range of properties. You kind of even get a flavor of that just from this particular image, because some of these you can see have like 5 planets sitting around. Some have multiple ones that are sized basically the size of Neptune and, Jupiter. Some have ones that have, multiple hot planets basically stacked up next to each other. So there's a ton of information that we've learned from Kepler, and then obviously succeeding missions as well. And I really do encourage you to take a look at some of these studies that looked at populations of planets that tried to say, well, what do planets look like fundamentally? In fact, Kepler was one of the missions where, along with ground-based observations, you can start to constrain this idea of how many planets are there per star, how many Earth-like planets might there be per star. And in addition to basically these large-scale demographics, like I mentioned before, Kepler also started to find planets that are likely in their system's habitable zone, which, for those people who are interested in looking for life and trying to understand basically how habitability evolves on different worlds, that's a really, really exciting thing, because all of a sudden we have targets now. In addition to kind of understanding these planets, one other thing that Kepler did that's really, really important, and I'll talk a little bit more about why this is important later too, is that the really, really highly sensitive, long baseline and continuous observations of the stars, because they're basically observing these stars, hoping they'd find transits, also meant that you were able to track the activity and rotation of stars in a way that was never done before. So Kepler was also a great stellar astrophysics mission and did an excellent job of being able to, for example, look at stars that flared. So we've learned a lot about how often stars flare and what type of environment that might create for a planet around a particular star, and really how that activity varies as a function of stellar type too. So Kepler was, because it has this really incredible data set, is still responsible for basically making all these discoveries and learning about all these really interesting things about star systems, and then perhaps the planets they also have around them. So one last thing I'll mention, and this is why you saw those additional number of stars that Kepler basically was able to observe. So Kepler had a number of reaction wheels that kept it pointed at the specific field it was looking at, but eventually one of the reactions wheel failed. And usually you might be like, oh, if a reaction wheel fails, well, it sounds like that's it for the mission. But in the case of Kepler, one of the really cool things is engineers actually figured out a way to use the remaining reaction wheels and then use solar pressure, so pressure from the photons from the sun, in order to balance basically the pointing for Kepler. So they were able to control Kepler, and what they basically had to do was just point it at different regions of the sky to keep it balanced as a function of the sun angle to the actual telescope. So once they were able to do that, they actually had a new mission, which is called the K2 mission, where they would now start looking at different fields as a function of time of the year. And they were able to search completely new regions, obviously for much shorter periods of time, for exoplanets, and really conduct science in a bunch of other things too. So people did a lot of really interesting solar system science and other types of science as well. And Kepler was able to do that even as it was having parts of the telescope that were starting to break down. So it was really a testament to how powerful this telescope was, which is really amazing when you consider that this was a telescope that was, again, just conducting photometry using one particular band. Part of this, I think, should make you think about the fact that if you just have a telescope that's staring up at, the sky, that's looking out at basically all these stars, there are so many planets out there that you will just start finding them as long as you have pretty good optics, you have pretty good sensitivity in your instruments. And that just shows you how many worlds there are out there, which is why obviously, Ravi and I, and probably all of you, are excited about exoplanets. So I'm going to talk about a little bit about the successor in some ways to Kepler, which is the Transiting Exoplanet Survey Satellite. Before that, if there are any questions, feel free to raise your hand. I can go ahead and call you. But I will just go ahead and start otherwise. So the Transiting Exoplanet Survey Satellite is in a lot of ways the successor to Kepler. It launched in 2018. It's still taking observations, and it's a little different. You'll notice here I put down that TESS basically has 4 cameras that have about 0.1 meter apertures, and it conducts observations, again, in the visible. So pretty close to Kepler in terms of that bandpass. But it has a pretty unique orbit. It's on this kind of 13 and almost 14-day really elliptical cislunar orbit. And what that lets it do is it basically lets it carry out an all sky survey. So it looks to look at basically the entire sky. And it does that during its primary mission. It did that by first looking at the southern hemisphere, and then looking at the northern hemisphere. And basically these 4 cameras are set up so that when it points at a particular region of the sky, it covers basically these big blocks of the sky. And it has a pretty big field of view. So what that means is that whereas maybe some portions of the sky, it only observes for 27 days, so you can see that on the left, a lot of other portions, it actually overlaps from one region to the next. So that means there actually end up being regions where while it only might observe a particular region for 27 days, other ones it might start observing for much longer, depending on how much overlap happens. And in fact, there's a particular region that's near kind of like the poles, the ecliptic the ecliptic poles here, that you actually end up nearly getting full year observations. You're nearly continuously observing it. The other really exciting thing about that is that there's also a region of the sky that GWST can continuously view too. So that's really great, because all of a sudden, if you're getting really immaculate, if you're getting continuous data, basically along that particular region, that's where you're going to find the longer period of planets. That's where you're going to get more detailed information about a planet. And then all of a sudden, GWST can observe that planet as long as it's close enough, because it's always in a viewing zone. So you're not hoping you can try to schedule something. You're not hoping there are issues in terms of GWST being able to observe it. So basically what happened with TESS is it went through and in 26 different segments observed both the southern hemisphere and the northern hemisphere. And TESS was really interested in trying to look at, again, G, K, and M type stars that were pretty bright. And so because these are smaller telescopes, it couldn't get some of those fainter stars that Kepler could get. But it was able to get really great data on them. And it was able to look at regions that Kepler never really looked at or didn't have as ease of access to even during the K2 mission. Again, it was able to carry out astroseismology studies. But one of the key things is TESS was really focused on looking at the closest stars, and specifically M dwarfs. So M dwarfs outnumber every other type of star pretty significantly. So they really dominate the type of star that exists pretty close to our system. And TESS was able to basically start to monitor M dwarfs. And because remember, M dwarfs are smaller, so that means that the planets that orbited typically will be at closer separations. That means that you can probably look for whether there is a habitable zone planet, see if you can find multiple transits for a lot of the really close M dwarfs, because as long as you're observing for long enough, you will be able to catch those transits. Now, of course, there's a size limit on that. You need to have a planet that's big enough in order to actually be able to detect it. But that's one of the things that TESS is really effective at. And already TESS has discovered something over 280 new exoplanets, and it has over 6,000 targets of interest. So I know 280 doesn't sound that large compared to 6,000. I can personally tell you I'm working on papers with people who are leading them. And it's literally when you initially try to find a planet, you look for a transit, you probably learned this already, but then you really want to confirm it. You want to use other methods in order to confirm that what you're looking at is a real planet, not just some stellar signature or some instrumental signature. And I know there are planets right now sitting in, people's folders, and they have the confirmation data, or they're trying to describe stuff. And it's just a matter of getting those papers out and pushing them out there and announcing to the world that you found these new planets. So expect a lot more planets to be confirmed using basically these TESS observations. But TESS has already been discovering really interesting systems, including this system on the left, which is TOI 700. Initially, there were 3 planets that were detected, and people were excited because one of them, they're all probably pretty much rocky. But one of them was believed to have been in the habitable zone, and now the team's kind of looked back at it, and they found another planet that's actually probably in the habitable zone, depending on your definition of which habitable zones are most interesting to you. But of those 6,000 targets, over 1,300 of them have radii that are less than 4 Earth radii, which means that are at least, maybe Neptune-sized planets, but a lot of them might even be in the regime where they might be kind of rocky as well. So one of the really cool things, because TESS does such a great job at looking at these M dwarfs and then systems around them, is that TESS was really able to find a lot of these closely packed planetary systems that Kepler really found a ton of around these M dwarfs, and it started to probe these varying kind of orbital architectures. So it started to look at how does things like eccentricity, how do things like orbital resonances, how do they play out in basically planetary systems around the galaxy. TESS has also found several young systems. And again, this is by using basically moving groups. So that's by looking for planets around stars in groups of stars that they know the age of because of something like an HR diagram or because of other kind of age measures, including 2 planets that are in systems with ages of less than 150 million years, including one that's actually less than probably 100 million years. And that's really exciting because now you can imagine if you find a planet that's 100 million years around a G-type star, that's you know that the things it's been subjected to with respect to its host star, with respect to how it's evolved, how it's cooled, that probably is quite different than if you looked at it 4 billion years from now. So these are really potentially diagnostic systems in terms of understanding how these planets kind of evolve. So that really gets through a lot of the transiting surveys. So I'm going to take a quick little pause here and have a sip of coffee in case anybody has questions. And if you don't, that's fine. You can always ask them at the end too. All right, so I will go ahead. If you do have questions, feel free to raise your hands. Happy to talk about them. So the next, we're going to get into missions that TESS is obviously still operating, but we're really going to get into kind of active and future missions now to kind of round out these capsules. So the next one is probably a name that is familiar to you all, which is the James Webb Space Telescope. So this is a really exciting telescope that in some ways is kind of a successor to Hubble and Spitzer, but really kind of Spitzer in the sense that it's this really large telescope, 6.5 meters mirror, but it's the segmented mirror that you can see here with like the honeycomb pattern on the left. This is in the clean room at Goddard, and it has about 6 times the collecting area of Hubble, which means that all of a sudden you can look at a lot fainter objects, you can get much better precision on spectra. And it conducts observations in the visible and infrared using a number of different instruments that are optimized for both spectroscopy and imaging. And it does this from a halo orbit at L2, so the L2 Lagrangian point. And one of the real advantages of that is because GWST has this really big sun shield, and because it's at L2, it is capable of basically passively cooling nearly the entire observatory, with the exception of the mid-infrared instrument MIRI, which just requires an additional cryocooler. Now that's really important because you probably remember from the Spitzer discussion that Spitzer had to use a consumable. So that means that because it used liquid helium, once it used up that liquid helium, it was done. GWST is going to be able to last much longer in theory because it can kind of keep itself cool for using different methods that don't require consumables. So that means it has about a 5.5-year primary mission, and then it could even last for up to 20 years. Now, one of the exciting things, GWST, because it is such a powerful observatory, because it observes in all these interesting infrared bands and has this exquisite sensitivity, it actually is a multi-purpose observatory, just like Hubble was. So that means that it looks at galaxies, cosmological questions, solar system objects, but it also has multiple ways that it can look at exoplanets. So it's not just something that can look at exoplanets using transmission spectroscopy. It also has mass so that it can conduct coronagraphy. So it can use basically conduct direct imaging studies of exoplanets in order to both detect and characterize exoplanets. Now, GWST when it initially got launched, it first went through obviously commissioning of instruments and checking out of the observatory, making sure everything was working all right. But eventually, what it did is it actually started observing things that were first chosen kind of by the community. And it was a really cool program where basically it said, all right, let's have the community kind of decide on different targets within different fields. And let's use those observations in order to kind of test what can we do with this particular observatory. So that early release science was great because it let scientists know what exactly was going on, what GWST was to some degree capable of, at least at the beginning of its life. And since then, based upon guaranteed time observations and the initial observations from cycle 1, and I'm saying cycle 1 because GWST has open calls, just like Hubble has as well. you can, if you have a great idea, I do recommend there's a bunch of tools to figure out whether your idea is actually great. You can apply and you can say, I want to point this telescope at my favorite target in order to kind of study this question I'm interested in. So based upon cycle 1, so the first observations that were awarded, there have already been really, really great results that GWST has found. One of the more recent ones you might have seen in Nature a couple of weeks ago is that for a particular planet, WASP 39b, the combination of using multiple instruments were able to basically pin down nearly a half dozen different molecules, different constituents of the atmosphere. So these are kind of the instruments, the wavelengths that they operated in, and the top one kind of shows what types of constituents you can use those wavelengths in order to kind of probe. And one thing that you'll find is that obviously you can probe all these things and you can find out this chemistry, but once you know the context of the temperature and a lot of things about the planet's bulk properties, you can actually start to trace the formation and evolution of that planet based upon its atmospheric chemistry. So if you know the carbon to oxygen ratio, I'm sure you've gone over some of these types of things, you can start to understand, where did this form? Did it form past an ice line? Did it, how did it evolve over time? How did redox state potentially change? So JWST has already done that. It's also helped confirm an existing exoplanet candidate that is Earth-sized and rocky. And the initial results from the commissioning of the telescope and the instruments indicate that generally, when you look at these different types of instruments, so when you look at like NIRISS, NICMOS, MIRI, all these near-infrared and mid-infrared instruments, typically they will have basically unseen of levels of precision. So that means they will have incredible sensitivity that will let us probe smaller planets and really interesting questions. Whether we'll be able to probe Earth-sized planets maybe in the habitable zone, I'm not sure about that. But one of the things you find with these observatories is that you really don't want to discount how creative people can get and how they can learn how to use them in order to basically observe targets you never thought they would be able to observe before. So one of the exciting things too is now that cycle 1 is underway, and now that a lot of the guaranteed time observations are underway, JWST will observe the TRAPPIST planets. It will probably provide us really interesting data. There were already kind of presentations of some really interesting findings about some of those TRAPPIST planets in a conference in December. And I'm pretty sure, I know some of those are working their way through peer review. So you should expect to see papers on some of those soon. And also it's going to start a lot of these other surveys, a lot of these other observations I'd already kind of mentioned. So JWST is going to be a really exciting observatory that, keep your eyes open when you're looking at the news. And if you are interested in observations, start doing some research on the telescope and the instruments, and this is the time. There are a lot of ideas that have been thought of. There are way, way more ideas that have not been thought of. And a lot of them are going to be really, really interesting. So there's no reason not to be the people who are basically exploring them. So now we're going to get into missions that are not yet launched. And I'm going to start, and I'm going to be a little bit shorter about with respect to descriptions of some of these. I'm happy to talk about them more. If you have questions, feel free to email me as well. But again, as always, I'll have additional references too. All right, nice to see your hand. Great. Varun?
Yes, sir. I had one doubt. It was related to the detection. So in the previous lectures in the course, in lot of lectures, they mentioned that we mostly discover the planets which are the closest to the host star, right?
Yep.
So in a way, we are basically just discovering the Mercury of other solar systems. And I wanted the basic question is, how and why do we then expect for life to have originated on those planets? Because we should not expect, because the temperatures of the planets of the Mercury is comparatively higher in comparison to the planets which are outside which are far away than the Mercury, or far away than the closest 1 or 2 planets to the host star.
That's a great question, Ron, and you're absolutely right that typically the methods that we're looking at are biased towards finding planets that are closer in. And yeah, using the analogy of Mercury and the kind of equilibrium temperature, I think that's a fair thing in general to think about. But remember, we've actually come pretty far with respect to the planets that have been detected. So at this point, while the methods that we use to detect exoplanets are pretty effective at finding planets that are close in, that do have temperatures that are like Mercury, we are now finding lots of planets that are much cooler. So at this point, we're finding planets that have temperatures that are lower than the Earth. So it's important to remember that while a lot of the techniques to detect exoplanets are maybe most effective at finding close-in exoplanets, that doesn't mean that that is all they detect anymore. At this point, that's why you kind of see these newer observatories with bigger mirrors, with different observation strategies, with longer observation baselines, so that they can actually start to find planets that are cooler, and that are maybe more temperate and more hospitable to life. So while the question of how exactly life might arise or how it might exist on warmer planets is also an interesting one, and I think there are probably people who have answers to this, because there's people who think there might be evidence for life, there might be niches for life in their solar system at temperatures that are higher than the Earth. The reality is, for exoplanets, we are also looking at planets that are much more temperate, that are a lot cooler, and that are kind of more familiar with respect to potentially hosting life. So thanks for that question, Varun. I'm going to go ahead and I want to make sure I get through a couple of these slides. So just raise your hand and I'll call you at the end.
Another one. In the previous slide, you mentioned that the GWST denotes one rocky planet and Earth size. So I just wanted to confirm, did it conclude from the fact of the density of that planet, or was it because of something else?
Yeah, so I mean, this was a density one. So in this particular case, I think the observation, I don't know if it was a TESS observation. It's a Lustig-Jaeger paper that came out recently, and I'll have to look it up. I think it's a density confirmation. What technique they used to actually get the mass constraint, I'm not sure yet. I would imagine it was probably RV plus also some type of reflected light thing that they used there to put a constraint on the total volume. But it's almost certainly a density confirmation. So the next mission is that I'll go to, and we're going to go into kind of quicker discussions of these planned missions, is the Nancy Grace Roman telescope. So this is the first time we're really talking about something that was not transit heavy with respect to detecting exoplanets. So the Nancy Grace Roman telescope is a 2.4 meter space telescope. Should sound familiar. It's actually basically the same type of telescope as Hubble. That will operate in the visible and near infrared from a halo orbit around L2. And it has a couple different goals that are exoplanets. It has one non-exoplanet goal that's really related more to cosmology, but then it's planning to conduct a gravitational microlensing based exoplanet survey. So hopefully you all learned about microlensing, where basically the gravitational distortion of a particular background object occurs due to a forefront object, and you can actually have that enhanced. You can detect it. It's a lot easier to be able to constrain some of its properties. So that's one of the things that the Roman telescope will be aimed at. But the other thing that the Roman telescope will also have is a technology demonstration of a space-based direct imaging coronagraph instrument. So this is going to be one of the first times that basically we've tried to use a space-based telescope to block out the light from a star and then directly see reflected light or light from a planet that is in that system. So that's a technology demonstration. So right now it's basically just trying to show that we can get to this type of suppression of the starlight from the star, of the starlight, and then we can actually get to a contrast ratio. So we can see things that are, a certain ratio darker than that star in a particular region outside of the star. And the wide field instrument, while that's going to provide multi-band observations, visible to near infrared, the coronagraph instrument will mostly be over a smaller range in the visible. Now, the really interesting thing about the coronagraph instrument is that it will actually use deformable mirrors. It'll use mirrors that are constantly moving in order to adjust to the wavefront for the light. And as it adjusts to the wavefront of the light, it will basically create that starlight suppression technology in order to reach basically 10 to the negative 10 to the negative 8th suppression. So that means that you would be able to see something that's about a part per billion less bright than the host star. And that's the level of contrast at which you can start to actually directly detect and characterize gas giant planets. So that's aimed at launching in 2026, 2027. Definitely keep an eye out on that. That is a really exciting thing because that's basically the underpinning technology for another observatory I'll talk about, and for future attempts to try to directly detect light from an Earth-like exoplanet, which hopefully you've discussed why that's important relative to transiting science. So another mission that is going to be launched in the future right around the same time as the Roman telescope is the Plato telescope. So Plato is an ESA planned space telescope, and in this case, it has 26.2 meter visible light cameras, and it'll operate from L2. Now, Plato is going to be it's going to sound familiar. It's going to basically perform uninterrupted, high precision photometric monitoring of a huge number of stars for multiple years. And really the idea for Plato is to be able to conduct this exquisite, kind of like Kepler, not only detection of planetary transits, but also astroseismology of stars. So really Plato wants to be the mission that detects even more, a huge number of exoplanet systems, because it's just going to sit there, stare there, and try to find these worlds. And really it's going to be aimed at finding even more of these hopefully rocky planets in the habitable zone around these sun-type stars. So in general, Plato's trying to characterize hundreds of rocky, including a lot of Earth twins, icy and giant planets. And by having pretty good precision, by having basically precision so that you can tell the planet's radii by within 3%, its mass within 10%, and an age within 10%, based upon some of those metrics, based upon, for example, rotation, which I had mentioned before for the stars. Getting a little bit farther off now is the Ariel mission. So Ariel is again an ESA proposed mission. It's under development right now, and it's planned to launch right before the end of this decade. And it's basically a 1.1 by 0.7 meter space telescope that's going to operate in the near infrared and the visible as well, part of the visible. And it'll operate from an orbit near L2 again. And really, Ariel is meant to start to understand the chemistry of exoplanets and the chemistry of exoplanets of a wide range of types of exoplanets. So the idea for Ariel is that it wants to survey up to about 1,000 exoplanets at the same time in both the visible and infrared. And it's important to be able to get those visible and infrared observations, because that can basically give you multiple means of understanding the abundances of a particular constituents. So Ariel is going to have a number of photometric and spectroscopic channels, and it'll cover the entire sky every 3 months. So it'll be able to have access to a number of different targets over its 4-year timescale. So now we're getting to kind of the really farther down the road types of observatories. So the Habitable Worlds Observatory is planned to launch in the 2040s. So you have plenty of time to start to work on this and start to propose interesting ideas for it. And it's basically still a concept right now. So it is a planned serviceable 6.5 meter segmented mirror space telescope, so similar to James Webb GWST, that will operate in the UV, visible, and near infrared from near L2. Now, this particular observatory was recommended by NASA's 2020 Astrophysics Decadal Survey, and the planning for it is underway, including an initial technology development program, but it does not have its specifications fully basically put out so far. But the really important thing about this particular observatory is kind of in its name. It is aimed at trying to find Earth-like planets in the habitable zone of sun-like stars, of really solar-type stars. So it is meant to basically have the technology and ability to have, for example, mirror alignment, to have starlight suppression, so that it can achieve the contrast ratio, so that it can directly look at light from an Earth twin type planet. And it's really built upon a couple studies for concepts that have been commissioned by NASA recently, LUVOIR and HABEX. And it's going to really depend on the technologies that Roman is about to demonstrate. This is, in some ways, you can think about it as a mission that is going to use the technology and discoveries of Roman and kind of ramp them up so that they can look at even smaller planets and planets that are more temperate. And then the last the mission we're going to talk about now is just the LIFE mission. So this is a large interferometer for exoplanets mission. This is currently a mission concept that could eventually be picked up by ESA. So it's really just in the study phases. There's no real data attached to it. And the idea is to use, so you've noticed, if you want to find smaller and smaller, colder planets, you start to need bigger and bigger mirrors. So either you start to have really creative designs for these bigger mirrors, these bigger baselines, or you use something like interferometry. So in this case, they want to use nulling interferometry, using 4 telescopes with a 6:1 baseline array, so that you get basically an effective diameter of anything from 10 meters to 600 meters, with individual mirror diameters of about 4 by 2 to 3.5 meters. And the idea here is using that nulling interferometry and these really big baselines in order to conduct mid-infrared observations, so you can start probing the atmospheres and surfaces of these exoplanets. And that the reason why they want to do that is because they know there's a bunch of really interesting chemicals that have signatures in the mid-infrared that can basically be atmospheric biomarkers. So they might be the types of signatures for life or habitability. So the idea for life is that it would investigate something between 30 and 50 exoplanets with basically radii of 0.5 to 1.5 Earth radii, so things they think might be rocky, and that these planets are pretty temperate too. So that is basically the capsules that I have here for some of the missions. Like I said, those aren't all the missions. There's a lot of cool smaller missions. There's plenty of cool bigger missions and even current ones. And I encourage you to take a look at them. I'm going to very quickly talk about something, though, that I want to make sure I stress before I open it up to a couple minutes of questions. So one, we've kind of been talking about types of missions. And one of the things you've noticed probably is that they are very different in some ways. Some of them build upon each other, but they often have different ways in which they're trying to observe things, different wavelength ranges, different types of technologies. And really one of the driving factors in understanding planets around other stars and different types of planets around other stars is that you really have to have this creativity in not only technology, but also techniques, methods, and then also thinking about ways for just observing a planet doesn't necessarily tell you about the conditions it's been through and that it will go through. So sometimes you actually need context as well. And here I have a couple examples of kind of the techniques, kind of interesting technological creativity that people have had. So here's something that people do a lot in astronomy. So for example, if you have a bright star and you're like, oh, my CCD can't really stare at that. One thing that people have done, for example, use Hubble to observe specific exoplanets, is they've said, let me start scanning so that the light falls on more pixels. So all of a sudden, something that was bright, that was saturating a pixel, is no longer saturating my pixels. And now I can start to get much better photometry. I can get much better data. I can actually start to tell things about this world. Another example is for a technique is this paper by Agel et al. 2015, where basically that group said that if you look at observations of astrometry, so how the position of a particular star changes or a planet changes over time, and you recognize that the moon, if there is a moon, and the planet might be at different temperatures, the position of the object you're looking at will actually slightly offset depending on the wavelength you're looking at, because the SED is peaking at a different place. So that's based upon what wavelengths you're looking at and the total position, the difference in the position, you might actually be able to detect a moon and be able to constrain some of the properties of a planet and a moon. Now, this is something that probably requires technology farther down the road right now, but is an exciting way of kind of thinking about how can I combine this kind of creative approach to try to detect something that really hasn't been detected at this point, which is like exoplanet moons, which with respect to at least kind of a concrete confirmation. But and the last one that I'm going to show in this particular slide is this idea that also, if you think planets have magnetic fields, just like we know they have them here in our solar system, then you should have interactions between a star and that planet's magnetic field, which means you might want to look for radio emissions from a particular system, which, for example, this group led by Turner et al., Jake Turner et al., have been looking for a lot of different systems. So the last thing I'm going to go over really quickly is that creativity. So that doesn't mean when you're trying to understand an exoplanet, understanding the things around that exoplanet and other contexts is also very important. So for example, in the top left is an example of how spots on a star can sometimes mimic an exoplanet. So here you kind of see that top one with an exoplanet. This is what kind of peak a transit would make or whatever else. And you might think, oh, maybe that's a moon. Maybe that's something cool like that. But it turns out that, or maybe that's a second planet. But it actually turns out that if you have spots on a star, which are very common, our sun has plenty of sunspots, that can actually mimic exoplanets. So understanding how stars kind of vary is really important to understanding whether you're really finding an exoplanet and how it changes. Similarly, if you want to try to understand a planet and try to figure out what its atmosphere is like, but there's a disk of debris around a star, that also can kind of affect the noise properties and whether you're making a legitimate detection. A really important thing to think about, stars are really, really important to understand if you want to learn about exoplanets. And that's because they control what type of spectra you're going to end up finding that can help you characterize an exoplanet, but also because the processes that occur due to the star, such as stellar activity, such as coronal mass ejections, the solar wind, different types of radiation, they're going to affect the likelihood of life on a planet. So that is an entire subfield that is really important. That's really interesting to kind of learn about, not only for exoplanets, but even for the planets in our system, because our star has probably evolved over its lifetime and has probably affected the ability for planets in our solar system to host life. So the last thing I'm going to mention is that, to some extent, I'm telling you, all right, you should use radio observations, use UV observation. You should, think about all these really cool things. So are all missions or all observations really exoplanet missions? Maybe not all, but I think a lot of them are. And the way you can kind of think about that too is at this point, scientists now realize that one of the best ways to study exoplanets is to study planets and moons in our solar system. And that's because the planets and moons in our solar system, one, we can get much higher fidelity observations of them, but also we can, as we learn about them, then we can start to look at planets that are similar to them outside our solar system, and we have a better way of interpreting information about those planets. In addition to that, we can also start to learn about how planets in our solar system evolved over time. We know the Earth changed over time, so understanding how it might have changed lets us know what to look for and how to interpret planets that might be at that stage that are not in our solar system. For example, one really cool thing is we should be looking at the Earth over time. So for example, when you look at the Earth, this little picture in the bottom left is using the Discover satellite, which is a NOAA-driven satellite. And that shows you, unsurprisingly, we were all familiar with this. Not only is there land and water, but there's clouds and weather. And that means that the face of the Earth that we see changes over time. And that is what we should expect to see for Earth-like planets in other solar systems as well. So understanding how the face of the Earth changes due to weather, due to other processes like volcanism, due to other things, that will help us understand how to find and interpret data from other Earth-like planets that might potentially have life. Finally, the last thing I want to mention is that you see this little satellite here on the right, which looks very different from some of the other ones. One of the real cool revolutions, I think, in astronomy has been that you do not need to have a multi-billion-dollar, multi-meter telescope in order to do exoplanet science anymore. There are now multiple missions that use much smaller telescopes that would fit in the size of a mini fridge or the size of a TV. And that can do really interesting targeted observations of exoplanets. And they cost way, way less. So the ability to actually probe and understand other worlds is no longer restricted to a small number of people or to, a particular type of technology that might be out of the grasp of a lot of other scientists who have great ideas. So hopefully that means that, if you have an idea, if you've been thinking about stuff, or if you want to learn about the things you can do, I strongly encourage you to start to look at things like CubeSats and SmallSats and think about how they might be able to be used to kind of answer these questions too. So I think that's the last slide I have. I know I kind of ran up close to the time here. I think we have about 5 or 10 minutes for questions, or maybe probably just 5, but happy to take those. My email is also just my first name, my last name at nasa.gov. Feel free to look me up and shoot over any other questions you have to. Thanks, everyone.
Yeah, thank you so much, Dr. Prabal. So if you have any questions, please ask. Please unmute yourself and ask.
Hello. Can you hear me?
Yes.
Yes, I can.
Yes. So it is very exciting to know all about the prospective telescopes that we are going to send to the space. So my question is, how do you test those telescopes? I mean, in terms of their credibility on the correctness of the data they provide before it is finally set up in its orbit? Or you test those only after you place them in the orbit?
So that is a great question. And, this is the type of thing where I don't know the background of everybody in this lecture. This also kind of shows the different roles that you need to play, that you need to have when you conduct a lot of astronomy and exoplanet science, because you test them both before you launch them and then after you launch them. So for example, when you are basically every part of these telescopes, whether it's the telescope, the instruments, you first test them at a component level, and you say, hey, for example, if I have a particular detector, let me set up a light source that I know how much light it puts out in this wavelength range, and then let me use my detector to detect it. And let me make sure it's giving me the correct value. So you do a lot of calibration and testing on the ground, and you do it at the component level. Then after you do it at the component level, then you put it all together and you try to do testing on the ground when it's combined, so that you make sure that you're still seeing things that are calibrated and that are correct. Then when you launch it, the first thing basically every mission does is they first have a commissioning and calibration period. And during that period, they're doing exactly what you kind of alluded to, which is that you are going to be looking at either internal stuff or at a source that you know really well. So let's say there's a star I know the spectra of really well from other observatories. I will point my telescope at that first, and I will say, can I get the same data? Is the data correct? Is it off in some way? What are the adjustments I need to make? Are there problems? That's actually why, for example, they needed to correct some of the things on Hubble. And then once you do that, you kind of learn the performance of the instruments, and that's what drives kind of how people interpret data in the future. But that's a great question. So you're actually testing the entire time through, typically for these missions.
Okay, so we have one more question by Raghav Narasimha. Do you want to unmute and ask, Raghav? Okay, I can read it out. Is terrestrial planet finder coronagraph renamed as Nancy Grace Roman, or is it a different one?
So yeah, so the terrestrial planet finder, a coronagraph mission concept, TPF. So that is actually different. I do not think that is Nancy Grace Roman. I believe, let me just check this really quickly. I'm pretty sure that is an interferometry mission concept, TPFC. Because I think I know people who worked on that. Yep. Let's see. Oh no, TPFC is a chronograph instrument, so I do not think.
So, Prabal, are you?
Yeah.
Is the question? What's the question about?
The question is whether TPFC is Roman. So TPFC isn't Roman.
No.
Yeah. So TPFC is not Roman. I'm just trying to think about whether TPFC I think is really more of a precursor for HAB roles. I think. I'd have to go look up some of the information for that, but Roman I would really think about as kind of an initial step to chronography, to space-based chronography. So you're talking about getting to detection thresholds that are basically going to let you have access to exoplanets for the first time, but are not quite in the range of the rocky exoplanets you'd be looking at for kind of those future concepts. Ravi, do you have anything else to add?
I think that's good.
And I think if there are, and like I said, if there are any other questions, feel free to email me. I'm happy to answer them. It's fun to talk about these missions, and hopefully you all start finding a bunch of cool things too. And I get excited that I'm like, oh, there's all these discoveries and characterization. Because like I said, I'm greedy about exoplanets, and I definitely want to learn more.
Thank you so much, Dr. Prabal. It was a very interesting session. Thank you for accepting our invitation and giving a talk in this series. Thank you so much.
Yeah, it was my pleasure. Thank you.
Thank you, Prabal.
Thank you, everyone. Yeah, Dr. Ravi, would you like to say something?
Oh no, I was just thanking Prabal, and that's about it.
Okay. Thanks everyone for joining. Tomorrow we will be having the last session of this course. So yes, do join tomorrow. We will be having a very small session about feedback and all at the end. So thanks. See you all tomorrow.
Have a great evening, everyone.